after it. Admit. Okay. Chat. Chat list. People. Okay. We will start with the seminar, and I have just a couple of information before we start. First is just to remind everybody that the RGIK will have a special meeting during the EGU, the European Science Union. So we already reserved a room for a meeting of around 2 to 3 hours during Monday, 15th of April, during the EGU in Vienna. So for those who will be around, everybody's invited. We will send the details shortly about this meeting. And the second information, there will be soon a call for a RGIK logo. So as you know, we don't have an official logo, so there will be a call for a logo. So those people with the graphic skills are happy to contact us after. And then today, it's a pleasure to me to introduce you to Julie Wee, a colleague of us here in the University of Freiburg, PhD candidate. She has been working in the group, in the RGIK action group since the beginning. I assisted all the meetings, and now she will be happily presented her work into the rock glacier in Gruben. Well, the whole Gruben site. So I think the floor is for you, Julie. Thank you again for accepting to present your work, and you have between 15 to 20 minutes, and then we will have around 5 to 10 minutes of questions after Julie's presentation. So the floor is yours, and thank you again for the giving us the seminar.
Well, thanks a lot, Seba, for this nice introduction, and hi to everyone. It is a pleasure to be presenting here in the RGIK seminars. And well, today I will be presenting some recent results that I have on the Gruben rock glacier and debris-covered glaciers to basically understand this, to better actually understand the seasonal surface dynamics of a rock glacier through the assessment of ground ice content and origin. Oh, so here, next slide. So just to give a bit of the context of the research here, so in the recent years, there has been, through the IPA action group, there has been focused international efforts to coordinate the development and compilation of rock glacier inventories. And well, rock glaciers can be quite simple textbook example landforms, for example, here in the Val d'Aqua rock glacier, which manifest, let's say, the essential features, geomorphological features, geometries, and flow patterns that, yeah. And but for other examples, for example, here in Gruben or here somewhere in the Andes, the determination of the rock glaciers is sometimes a bit more complicated, as sometimes we have beyond simple either or morphologies in the context of formerly glacier-connected rock glaciers or glacier forefield connected rock glaciers, where, or also other examples of multi-unit rock glacier, etc. So this is why it is important to also focus some efforts on site studies to actually better understand also the internal structures of these landforms. Here, in the context of for example, glacier-connected rock glaciers or glacier forefield rock glaciers. This is the context in which we will be in today. We can actually find different subsurface configurations. In the case of glacier, glacier-connected rock glacier or glacier forefield rock glacier, for instance, we often find such configurations where we have massive ice lenses that are of glacier origin that are embedded within the permafrost. And whereas here, this would be typical, let's say, a borehole section within a simple case textbook rock glacier where we have the permafrost, the frozen body here. And this would be the context for glacial landforms, so debris-covered glaciers in this case. So in this study, we have two aims. So first of all, to characterize the ground ice content and origins through geophysical surveys. And here in this case, in the past 2 years, we did extensive electrical resistivity tomography surveys. And last year and 2 years ago, we also did some refraction seismics on the site in order to actually characterize the ground ice content in a quantitative way. And the second objective here was also to assess the seasonal kinematic response of a rock glacier to subsurface properties. And with this, we actually did different types of geodetic surveys. So there was in situ geodetic surveys with the terrestrial ground survey, so seasonal monitoring approach, but also the installation of permanent DGNSS stations for much for a high temporal resolution with hourly monitoring, and also to also grasp the spatial to have a better spatial resolution. Also, we did together with Seba also UAV seasonal UAV surveys. So here with this map, I want to give you an overview of the field site. So there are many things going on, as you can see. So we are in the Swiss Alps here in the Saas Valley at a site called Gruben, where we have here the Gruben Rock Glacier, and adjacent to it we have the debris-covered tongue of the Gruben glacier that was also investigated within this study. And as you can see from the hatch lines, the rock glacier has quite a complex history because during the maximal extent of the little ice age maximal extent of the Gruben glacier, there was an interaction phase between the glacier ice and the permafrost. And here, with all of these measurements that you can see that were mapped on this image, we really want to really grasp a complete image of what is going on actually on this rock glacier, and what type of ice do we find within the rock glaciers, and how do they actually impact the surface dynamics. So here I will give you a brief overview of the ERT profiles that were performed on both the rock glacier and the debris-covered glacier. Here are the profiles. So we did a roughly 1 kilometer long ERT profiles where we can actually very nicely see resistivity, different resistivities in the different zones of the rock glacier. So in the what do we call the complex contact zone, so the former contact zone between the glacier and the rock glacier, we actually observe very resistive ice patches, for instance, here and here, while in the intact zone of the rock glacier, which would be in this area, we do still observe highly resistive layers, but the main difference is that it is located underneath a roughly 7-meter thick layer of coarse debris. To complete actually these surveys, we also, as I mentioned earlier, also performed a refraction seismics. Here, actually, we did it at 4 different places, but this profile is not shown in the scope of this presentation, but I will be mainly presenting profile 1, 2, and 4 that are presented here. And what we can also see here from the refraction seismics, in particular for the profile that was performed in the intact permafrost zone, is this very nice, very clear actually layer with a slower, let's say, velocities, which is a typical signature for an active layer. While this layer is much less pronounced in the other profiles. So together, with the ERT and RST datasets, we applied the petrophysical joint inversion scheme to actually retrieve the different phase fractions, so water, ice, rock, and air. And here we present only the fractions of water, ice, and rock content for these 3 different profiles. And what is interesting here that we see is that in the complex contact zone, we have quite a widespread ice content, in particular here, which is the area which is adjacent to a former thermokarst lake depression, as we can see here, the thermokarst depression here. So really inferring that there are still quite some massive, some remnants of buried massive glacier ice within this area. While in this zone here, in the intact zone, here we can see that we do still have, of course, quite high ground ice content in oversaturated conditions. If we look also at the rock content, which is also relatively high. So now that we have an image of the subsurface of the Gruben Rock Glacier, we went a bit higher up and we performed UAV surveys to really grasp this spatial image, general overview actually of surface displacements. And what is quite interesting with these results is that we have a seasonal signal where in what is here considered as the complex contact zone, during the winter season, movements are quite, displacements are quite low, while in the intact zone, the surface displacements vary between half a meter to 1.5, roughly half a meter to a meter. And at least that's for the rock glacier, and for during the summer period, surface displacements are much higher in the in the complex contact zone, and velocities are faster also in the intact permafrost zone, which is actually expected for a typical rock glacier. And if we compare actually this spatial heterogeneity in terms of the kinematic signal of the rock glacier, what we see here with this graph here, this map of the difference of digital elevation models. We can see that during the winter season, actually, the surface elevation changes are practically non-existent. I'd say in the contact zone here, while in the summertime, the signal is much stronger, where we have a much stronger vertical changes, which in this case is likely due to ice melt induced subsidence. And what we can also see here now, if we move on to the debris covered glacier, is this very clear spatial signal, kinematic signal here. In the lower part of the debris covered tongue, here we can see that during the winter season, horizontal surface displacements are relatively low compared to this section of the debris covered tongue. And this is likely explained by the debris cover thickness, which is much greater in this zone than here. While during the summer, well, here we have again very high surface displacements, and here a bit higher, but not as high as in this section here. However, what is interesting to observe here is that during the winter season, vertical elevation changes still occur, and as I said, there's this quite important debris cover thickness, which explains also the thermal lag that during winter, that even though the temperatures are colder, the heat is still transferred within this. The summer heat is still transferred within this layer of debris. And we also, from the permanent GNSS, we were also able to capture nice kinematic patterns in the complex contact zone. What we can see is that by comparing the kinematic data with ground surface temperature measurements, is that also that during the freezing period, the winter period, where ground surface temperatures are below 0 degree, there is practically no vertical surface displacement, and vertical surface displacement occur shortly after the zero curtain period, and this is observed for both cases. And also, once ground surface temperatures become slightly warmer, the velocity also increases here. And this we can nicely see here with the displacement profiles, where here during this cold period, the winter period, there's no vertical losses, and once the zero curtain period is over and temperatures become warmer, we observe ice melt induced subsidence here in both cases. And this is not the case in the periglacial zone, where we have this continuous creep behavior that we observe with with seasonal velocity peaks at the beginning of the melt season, and also during mid-autumn. While on the debris-covered glacier, what we see here is this continuous displacement that even during winter, this vertical loss is still observed. And as I mentioned earlier, this is likely due to this very thick debris cover that we have on the Gruben debris-covered glacier here. So basically, to sum up, what we observe from these all of these measurements is that in the intact permafrost zone, that we have this continuous creep with the early summer peak velocity peak, as well as a mid-autumn velocity peak. And also, what is interesting here that we observe is this that we have an ice-rich layer of permafrost at depth, which actually infers that the rock glacier was already under permafrost conditions before the little ice age advance. And also, well, in the complex contact zone, what we see is that we have a clear ice melt-induced subsidence, which is due to the melt of these massive ice lenses that are still present in this zone. And in the debris-covered glacier, we have a different signal, that we have a continuous vertical displacement even during the winter season, which is likely due to this thick, coarse, blocky debris cover of the on the glacier. So with this, I would like to wrap up my presentation, and I would like to thank you for listening, and happy to answer your questions.
Thank you very much, Julie, for this very nice presentation of the Gruben site. I think now we have time for questions from the public, and either raise your hand or unmute your microphone. But the first question is from Colin. Colin?
Yes, sorry, that was actually a mistake. I wanted to to clap and
To clap.
the presentation. Yeah.
Okay.
Sorry.
No problem. Lynn, it's not a mistake, of course.
No, it's
No.
not a mistake. Thinking, if there is no question, I can always ask one. I think it's really nice, comprehensive data sets you have. It's really fun. And then in the context of the first slide you showed regarding the inventories and RGIK guidelines, would you be able, with all the data you have, to put a line where is basically if you would have to outline what is a rock glacier, what would you do on the map, the first map you've shown? I guess it's not easy, but it looks like, because the last graph you shown, it's that it's a continuum, and the question is, our guidelines are not accepting that in a way. So if you would have to do the exercise in this region, where would you set a line, basically?
So so maybe also for your point on my last slide, maybe it's in terms of presentation that I've kind of put these two circles together in terms of, it was mainly in terms of processes that I meant, and it's not a debris covered glacier continuum with the rock glacier, because here actually it is quite, I mean, for me it would be quite straightforward to set a delineation of the rock glacier. Maybe I continued here a bit, but until the moraine here, and that would be it. And this is a completely different landform, which is a debris-covered glacier. But with this imbrication, I don't know if it's a word in English, of this of my two circles, then this is what I meant with the where we have periglacial processes, but also processes that are linked to the former presence also of the debris-covered glacier with this embedded dead glacier ice within the permafrost here. So that's what I meant. Sorry if it was not very clear.
No. It was just that what I misunderstood is probably that the complex compact contact zone was also embedded in what you map as a rock glacier. That was maybe what I misunderstood.
Yes, yeah, because it is part of the rock glacier since yeah.
Yeah, cool. No, that's interesting.
But with the data, at least with the geophysical data, what was maybe easier to a line that was maybe easier to draw was the delineation of the complex contact zone and the intact zone, where we could really nicely see this these differences in the subsurface. But I think also with the kinematic data, it really showed a very clear signal, where here we have also this back creeping behavior and surface changes, the absence actually of elevation changes in winter, whereas here there's this continuous creep in this zone.
Thanks. Do we have another question from the public? Oh, either by the chat or raise your hand. Cecil, please go ahead.
So I know a bit more than what you presented, so I'm asking a question about some extra data. No, because all the data, it's great, it's amazing, and then but it's also like a repetition of something that was done previously. Maybe not the long profile, but you also had older ERT or resistivity data on the rock glacier. And my question is a bit: do you see in the complex contact zone and in the intact zone some different behavior temporally, also in terms of ice content evolution or resistivity evolution? I don't know.
So actually in Gruben there were some geoelectric profiles that were done in the, if I'm not mistaken, in the 70s, and also some refraction seismics a bit later in the 90s. But unfortunately, I was never able to compare the data sets because, well, the location on the maps were not very, very, very clear for me to actually do the exact same profiles, even though I tried. But yeah, that was a limitation, I guess. But from what, but I can actually say a word maybe not on the internal structure changes, but on the surface dynamics, because surface displacements, because there were many studies that that worked on this site. So so there's a very long time series there of surface displacement measurements. And well, what we see here is maybe if I go to this slide, is that there's the kinematic pattern really with the flow field over the years really remained the same. But what has been maybe observed in the recent years is this the debris-covered glacier tongue really decelerating velocities. So meaning that there's really this decay of glacier ice. So really this thinning of the glacier ice, which was actually observed from our side, but also from Isa in her paper of 2 years ago now. Yeah.
Yeah, thank you, and sorry for the bit overstatement, but it's
But maybe you were
interesting.
thinking of another side.
Yes,
Yeah.
probably. No, but also
Right.
it would be very interesting to know kinematically in terms of processes, what's the future or then the difference under climate change of these two areas. So maybe future research.
But maybe, yeah, something that like a question mark that we could have is that with this, where is it? Here, this area where we have this very resistive layer, which expresses, which actually means that it likely is embedded glacier ice. Is it possible that to have a development of a new thermokarst lake here, for instance? But these are really open questions that would be worthwhile investigating in the future.
Thank you. Do we have another question from the public? Comments? Wilfried, please go ahead. Unmute yourself.
We cannot hear you.
We cannot hear you.
Yeah. It's better now. Okay.
Yes.
It's okay.
Congratulations. Yeah, these are beautiful measurements. And if you go back to the slide you just showed before with the velocity field, vertical and horizontal, I think we see a very clear difference. Yeah, at the left, we see that the flow field of what we call the rock glacier, which is clearly recognizable as a landform, the flow field is much more homogeneous and coherent. And on the debris-covered glacier, it is much less coherent. So the same applies to the contact zone. There, the flow field is much less coherent. And also the vertical displacements, they are much less coherent. So if we have really to classify a landform, the problem is a little bit that we classify a landform, which is a mental construct. It's not a natural phenomenon. It's a mental construct. It's in our head, right? It's not in nature. And this, or let's say, it depends on our perception, how we perceive a structure in nature. And the decision is to some degree is subjective, of course, because it's a matter of perception. And I would say that if you look now at these excellent velocity data, it helps you to quite clearly define what is the rock glacier. This is the homogeneous and relatively constant over time flow field. And what is heterogeneous is the debris-covered glacier. And the third zone is neither a debris-covered glacier nor is it a rock glacier. It can only be perceived as a contact zone, a complex contact zone. And I think that the problem is that such contact zones have no place in glacier inventories, neither have they a place in rock glacier inventories. They are contact zones. Yeah. So this is my view of the whole thing. But I would like to congratulate you again. These are fantastic results. And especially, I think that in such critical cases, the application of modern technology, geophysical soundings to know what is beneath the surface, and of course also the kinematic investigations, they will help us to better understand and to better delineate the forms we can really classify. So, bravo.
Thank you.
Thank you very much for your insightful comments and answers to Julie's presentation. And do we have any other question or comments for Julie?
Colin has the hand up
no,
again.
it's a mistake.
And she's still clapping.
She's still clapping. This one in the chat, I think. Okay, I think Jan also. Can you go ahead, Jan, please?
Okay. Can I add something about the old measurements? Okay.
Yeah.
Okay. Yeah, Jan, you can wait a little bit, please.
Yeah, because I have been involved in the measurements. I'm old and I have been involved in the old measurements. Right. Okay. So the resistivity soundings, they were point measurements. Okay. They are very difficult to compare with the tomography you are applying. But nevertheless, well, they are much less precise also, because they are integrating over quite a large spatial dimension. But nevertheless, in principle, they provide exactly the same result as you have. Let's say in a semi-quantitative way, the permafrost is still there, it is still thick, it may be a little bit warmer than at that time, but in principle it has kept the same characteristics, which is really a very strong indication that permafrost has a very a long way of reacting to climate, because the heating in the ground by thermal diffusion is such a slow process. And the seismic soundings, this is a little bit different. This is with the hammer, has been done with the hammer, so it was relatively shallow. And I think that also the velocities you show and the velocity variations we had at that time, they had been indicated in the publications quite clearly. They clearly show that, again, the ice content is variable in space. This is also a marked difference to the debris-covered glacier, which is homogeneous concerning the ice content. So direct comparison is perhaps a little bit difficult, but nevertheless, it can be confirmed now that your excellent measurements today, they confirm what has been interpreted, measured and interpreted almost 50 years ago, 40 years ago, yeah, right, in the 1980s. The radio echo soundings, okay, there are also radio echo soundings, you may remember, in the publication by King et al. In 1983, I think. They also confirmed that for electromagnetic wave, the glacier ice of the glacial tongue, the debris-covered glacial tongue, was very well transparent, but the permafrost was not transparent. So there is, again, this very clear difference. So qualitatively, I think you have a very important long-term observational result.
Thanks.
Thank you again for the long-term insights of the Gruben site and the measurements and the story behind them. Fascinating. Jan, you wanted to have a question?
Yes, thank you. Thank you, Julie. A very nice presentation and very informative for me. I am curious about the data interpretation part. Maybe I have missed part of your interpretation because it's late here in Hong Kong. My question is, because I noticed there is a big difference between the complex contact zone and the debris-covered glacier regarding the vertical changes. You mentioned that the vertical elevation changes on debris-covered glacier is continuous all year round. However, for the complex zone, the vertical changes stopped during winter, stopped or it's remained as very small during winter. So I'm wondering what are the possible mechanisms behind this difference?
Thanks a lot for your question. So I think that from the geophysical data set, what we can say is that also there's a big difference in terms of the thickness of the debris cover. So for instance, here in the complex contact zone, as we can see here, the debris cover, I mean, of course, the first few meters are not measured by the geophysics, but nevertheless, the thickness of the debris cover is quite small, I'd say. It's quite thin in comparison to here to the debris cover thickness of the debris covered glacier. So so the vertical changes, what we can say here is that they're clearly they have a direct no, sorry, the ground surface temperature, they have a direct influence on this kinematic behavior, at least for this part, because as we can see here, once the temperatures become higher, become warmer, the vertical changes. I mean, yeah, ice melt induced subsidence is initiated, right, in both cases. Whereas in the for the debris covered glacier part, since the thickness is much more important, there's a thermal lag, which actually explains that during the winter period, there's this continuous but less pronounced, continuous but less pronounced, I think that's important to mention, vertical displacements. This I know. Well, this is the winter period. Maybe that's not clear, but because I added this figure very last minute. But the bigger dots actually represent the beginning of autumn, so the 1st of October here and here. And these are bi-monthly. Each dot represents there are bi-monthly measurements here. Sorry.
Thank you. Thank you for interpretation. I have no answer to this question. Just intuitively, I would expect that a thicker debris cover help preserve the buried ice. Not the other way around. But I have no answer to this question. But your data is actually excellent. Thank you.
Yeah, I guess that this is a question also of the debris cover thickness, the threshold actually of the debris cover thickness. And here in this case, also maybe there's the possible influence, of course, of heat fluxes, of lateral heat fluxes, maybe. But this is a very speculative, right? Because here this data set is actually very close to an ice cliff, so there's maybe also this influence, but also, I mean, the vertical displacement here is not solely due to ice melt, but also to the downslope movement of the glacier.
Okay, thank you for your answer.
You want to add something else, Lynn, or?
No, well, actually, it's kind of what you just said at the end. Usually, in my understanding, that is what is the explanation of the difference in behavior. Is that in the complex part, it's rather a vertical source subsidence that is explaining the vertical displacement, which then is happening more in the summertime, while in the rock glacier, more classical rock glacier part, it's a creep process that is also happening during the winter, which include a vertical component anyway. It's a combination of horizontal and vertical. So that, at least I have no idea. You can correct me if I'm wrong, but that would be my understanding of it.
Yeah, and I mean that's totally right. And also, I think the surface, the terrain's topography also plays an important role also in the interpretation. In this section of the rock glacier, the topography is relatively flat-ish. And also here also actually if we now really focus on the rock glacier, here the surface topography is a bit steeper, but yeah, let's say between 20 to 15 degree slope angle, and yeah, and then there are also different components, as you mentioned, Lina, that contributes to the vertical changes, which is either thaw or ice melt, but also the simple downslope creep displacement. And also here, what is important to mention is this extensive flow behavior pattern that we have. So which actually makes the thinning, also the gradual thinning of the landform.
Thanks. I have one question from the chat from the public. Is sorry, I don't have a microphone. So it's Marcelo Bernardin. Say hi. Thanks for your presentation. I would like to know if you had any technical issue measuring with ERT on ice rock. How did the presence of water affected your measurements, and what was your skin depth attenuation effect?
Okay. Yeah. So thanks for your question. So no, we did not have alarming technical issues with the ERT measurements. I think it's well, actually, on the debris-covered glacier here, the surface, the terrain surface is composed of very coarse and big blocks. So that was maybe the biggest issue, to actually get to the contact with the electrodes. But for the rest of the landform, there were quite some the electrode contact was perfectly fine. And I'm not sure to fully understand actually the last part of your question with the skin depth. So
the attenuation effect.
Yeah, this I'm not sure to fully understand.
The penetration of the signal into the ground.
Oh yeah. So let me read the question. How did the presence of water affect your measurements? What's your so maybe let me go back to this slide. So basically the electrical, I mean the investigation depths could be roughly let's say 30 meters, I'd say, for the long profile. But then also we use different electrode spacing. So In some parts of the rock glacier, it was a 5-meter electrode spacing, which actually allowed us to have a greater penetration depth. And for some sections of the rock glacier and also on the debris-covered glacier, we used a 2.5-meter electrode spacing, which then limits also the investigation depth. But then with this, we have also a better resolution for shallower layers. I hope I answered your question in the right direction, but
I think, yeah, I think that is what he refers to, skin depth. Thank you for the answer. I think, I know if Wilfried, do you still keep your hand raised, or Marcelo says thanks for the answer. No more questions from the public, or any last comment to Julie's presentation? Otherwise, I want to thank you again, Julie, for the presentation, and all the guests for having this active discussion in turn of the Gruben side. And I want just to remind you that the next seminar will be on 27th of March by Eliseo Flores. It will be Inventorying and Kinematics of Rock Glaciers in James Ross Island, Antarctic Peninsula. So you are all invited to the next seminar. With that, I conclude the seminar for today, and thank you again to you all